Hey everyone, welcome to this explainer. Okay, I want you to imagine Black Friday for a second. Think about millions of users hitting an e-commerce database at the exact same millisecond. Or picture an airline booking system getting slammed with thousands of reservations from all over the globe simultaneously. It's basically a digital stampede, right? So how do modern, highly distributed databases manage this massive, completely chaotic data traffic without quietly deleting your critical information? If you've ever wondered how these systems keep your data intact when multiple things are happening at the exact same time and doing it all without a central point of control, well, you're definitely in the right place. Today, we're taking a deep dive into the fascinating mechanics of detecting concurrent writes, tracking causality, and scaling systems with version vectors.
Here is what we're going to cover today. First, the leaderless data chaos. Second, defining concurrent writes. Third, the happens before relationship. Fourth, the shopping cart case. Fifth, scaling with version vectors. And finally, number 6, converging on consistency.
Section 1, the leaderless data chaos. Now, in a traditional single-leader setup, you have one central node that basically dictates the absolute timeline for the system. Every single write request has to go through it. And sure, that guarantees a perfect chronological order, but it also creates a massive bottleneck. Imagine if that one leader goes down or gets overwhelmed by a huge spike in traffic. Your entire application basically grinds to a halt while the system scrambles to failover. Plus, if your leader node is sitting in New York and you've got users in Sydney, well, they're going to suffer some pretty terrible latency just to write a simple update. We actually moved to leaderless architectures specifically to eliminate that geographical lag and to gain supreme fault tolerance. But there's a catch. By abandoning that central authority, we completely open the door to conflicting information. So how on earth do independent nodes agree on what happened first, second, or third?
Well, leaderless replication, which is super common in Dynamo-style architectures, means exactly what it sounds like. Literally any replica can directly accept writes from clients. There is no strict hierarchy here. To ensure a write is actually accepted even if some nodes happen to be down, clients will often send read and write requests to multiple nodes in parallel, which establishes a quorum. Now, this sounds absolutely incredible for system resilience, right? I mean, if one data center goes completely offline, another one just instantly handles your data. But it also creates a wild west of data entry. Because writes can hit different nodes at vastly different speeds, there's no single referee blowing the whistle to organize the plays.
Picture this scenario. Client A and Client B are firing off conflicting updates simultaneously to different nodes. Let's say Client A is setting a value X to A and talks to Node 2. At the exact same time, Client B is setting X to B and talks to Node 3. Meanwhile, Node 1 is completely unresponsive. Maybe it's hitting a sudden network partition, or maybe it's just temporarily frozen by a garbage collection pause. Because these requests are hitting different active nodes at roughly the exact same moment, the database's timeline just becomes a totally tangled mess. Eventually, a third client comes along and tries to read the value of X. The database pulls data from both Node 2 and Node 3 and gets completely conflicting answers about the true state of that data.
Section 2. Defining concurrent writes. So you might be thinking, hey, the solution is obvious. Just slap a timestamp on every request. And actually, that approach is a real thing called last write wins, or LWS. It's even a setting you can use in systems like Cassandra. But relying purely on the clock essentially means you are going to randomly delete one user's completely valid update. Here's a surprising and honestly kind of terrifying fact about distributed systems. Physical clocks are literally never perfectly synchronized. Thanks to unpredictable network delays, latency spikes, and just normal hardware drift, clocks across global data centers can easily differ by milliseconds or sometimes even full seconds. If you rely on a timestamp, a tiny clock drift of just 5 milliseconds could mean you overwrite a massive financial deposit with an older, slower withdrawal. Last write wins actually translates to arbitrarily throwing away concurrent writes. For something low stakes like website analytics, maybe that data loss is acceptable. But for critical records, it's a total disaster.
Here is the real kicker. Exact chronological time doesn't actually matter here. It's all about information awareness. You can actually compare this to the theory of relativity. Just like in physics, where two events separated by vast distances can't physically affect one another faster than the speed of light, in computer networks, two operations might be separated by a network delay. Imagine a packet traveling over a fiber optic cable from New York and another one from Tokyo. If event A happens in New York and event B happens in Tokyo before the data packet from event A can possibly arrive, They are strictly concurrent. It absolutely does not matter what the server clocks say. If they happen without knowing about each other, they are concurrent. Section 3. The happens before relationship. This brings us to our golden rule. An operation A happens before another operation B if B knows about A or depends on A or builds upon A in some way. This dependency is strictly defined by the actual flow of data. Depends on means a client actually read a specific value, modified it locally, and then sent it back to the database. If a client didn't read the latest value before making an update, it absolutely cannot depend on it. Imagine two people editing the exact same wiki page at the same time. If person 2 didn't load person 1's changes before hitting save, they aren't building on those changes at all. If neither action happened before the other, meaning neither was logically aware of the other's state, they are strictly concurrent. And that means we have a genuine data conflict that the system actively has to resolve.
Section 4. The shopping cart case.
Let's apply this to a really practical, everyday scenario, an online grocery shopping cart interacting with a single database replica. First up, client 1 adds milk. The database processes this, stores it, and, this is crucial, it returns a token marking this state as version 1. Client 1 holds on to this version. Meanwhile, client 2, who is entirely unaware of the milk, decides to add eggs. The server assigns version 2 to this action, but because client 2's request didn't include that version 1 token, the database knows for a fact that client 2 didn't see the milk, so it doesn't just blindly overwrite the milk with eggs. Instead, the server safely stores both items as concurrent. Later on, when client 1 adds flour, it explicitly sends back its version 1 token to the server, mathematically proving it is building upon the milk state.
So because client 2 had no idea about the milk when they added eggs, the server flags these actions as concurrent. Rather than picking a winner and arbitrarily losing someone's groceries, which would be awful user experience, the database essentially throws its hands up and says, look, I don't know which of you is right, so I'm just keeping both. It creates what we call siblings. These are basically parallel, conflicting realities of your grocery list. And these sibling versions are kept alive by the database simultaneously, completely sidestepping the silent data loss that would have guaranteed to happen if we use last right wins.
When we map out that happens before relationship logically, you can clearly see how the initial empty cart state branches out into two distinct causal histories. On one branch, you have milk and flour. On the completely separate branch, you have eggs and ham. These concurrent branches safely exist side by side until a client tries to read the data. When that read happens, the database just sends back all the siblings. It's then entirely up to the client application to perform a logical merge, kind of like mathematically unioning the two arrays of groceries together into one single cart, and then writing back a final unified list containing milk, flour, eggs, and ham. Causality is mathematically maintained, and absolutely zero data was lost.
Section 5. Scaling with version vectors.
Now, what we just explored works perfectly for a single server handling concurrent operations, but what happens when we scale this up? In a global, leaderless cluster with hundreds of distributed nodes, a single version number completely falls apart. It just can't track which specific node processed which write, meaning those causal histories get tangled instantly. To solve this, we introduce the version vector. This is a collection of version numbers. It's essentially a state matrix, tracked per replica and per key. Instead of a single number like version 2, the system tracks an array. So the matrix might show that replica A has seen 4 updates, replica B has seen 1, and replica C has seen 1. Systems like Riak use a highly optimized variation of this called dotted version vectors to handle node churn and network partitions. This dynamic matrix is the secret sauce that allows the distributed database to track intricate causality across the entire cluster simultaneously.
By tracking version numbers from all other replicas, the database can safely identify which incoming values are true overwrites and which are actually concurrent siblings. Think about how powerful this complex state tracking is. It allows you to read your cart from a server in New York, fly all the way to Tokyo, and safely write your updated cart to a totally different server there. The database just compares the matrices and knows exactly what data you've already seen. There is a trade-off, of course. Payload sizes definitely increase because these vectors physically grow as more replicas touch the data, but the benefit is absolutely monumental. Version vectors empower the database to correctly detect concurrency and protect your data without ever needing a single leader node to play traffic op.
Section 6. Converging on consistency.
All of this theoretical detective work ultimately drives towards one major goal: strong eventual consistency. By combining these version vectors with automatic conflict resolution tools like CRDTs or conflict-free replicated data types, replicas can eventually converge on the exact same data state automatically.
CRDTs are actually really fascinating because they rely on fundamental mathematical rules, like commutativity, to seamlessly merge data structures. Think of a simple counter or a mathematical set where items can only ever be added. Because those addition operations can happen in literally any order and still mathematically yield the exact same final result, CRDTs allow distributed nodes to merge siblings without requiring any human intervention at all. It guarantees that if two nodes have seen the exact same set of operations, they will be in the exact same state, completely unaffected by the chaotic order those operations might have arrived in over the network.
Let's wrap this up with the key takeaways. Leaderless databases trade the safety net of a central authority for blazing speed, high availability, and incredible system resilience. But to actually survive the resulting chaos of concurrent data updates, we have to realize that concurrency is about a lack of information awareness, not physical time. We have to abandon flawed physical clocks and instead use the happens before rule to map causality. Then, we scale that logical causality globally using version vectors across multiple replicas. When inevitable network delays cause conflicts, siblings safely preserve your data until a mathematical or logical merge can happen. Distributed databases fundamentally redefine the very concept of time to protect your information.
Before we go, I want to leave you with one final provocative question. If version vectors ensure no data is lost by faithfully keeping these siblings alive, who actually resolves the final, complex conflicts when simple math just isn't enough? Is it the database, or is it you, the application developer? It's a truly fascinating trade-off. Leaderless systems give you incredible resilience and zero downtime, but they often push the ultimate responsibility of merging conflicting realities right back onto your application code. Think about the burden of that logic the next time you're designing a distributed system. Thanks for joining me on this explainer, and keep learning.